Thank you, Ulrich, for your presentation. I'll ask for those who are asking questions in this microphone that speak very close to the microphone, because the people on the internet are complaining they are not listening to the questions. They can listen to the answers, but they are not hearing the questions. Okay? So like this, like I'm speaking, very close to the microphone. Questions?
Thank you, Ulrich. I was interested in your fatigue fracture surface. Looks completely. Do you think that could be entirely mirror region all over the surface?
At this level, we also questioned the same thing. Is there anything? Can we find? Of course, if there's a defect at the surface, or you find a pore or something, you could somehow say, well, the failure could have somehow originated there. But we do not find any indication of a mirror at this level. If we look deeper, of course, with the different techniques, field emission, SEM, for example, if we go deeper into the material, we might find some. But at this point, we are not so far to say there is a fracture, a really clear fracture origin as we see it from the fast fracture.
Just a recommendation. We have started looking at PMMA composite denture teeth in fatigue, and we're seeing the same thing. Saying what's going on here? We'd see a clear brittle crack pop in and arrest, and we didn't see anything beyond that. And finally, just fortuitously, the students started using the optical microscope and playing around with the light, and then we started to see the fatigue crack growth lines, the stepwise crack growth lines that were not visible in SEM, and were not initially visible in the light microscope either until we started to play with the lighting.
Yeah.
And then he found literature saying that the fatigue crack growth in PMMA is very difficult to see, and you won't see it in SEM.
I totally agree. That's totally right. With the light microscope, you can see a lot more once you have somehow reflections in the material. Yeah, that's right. That's right. Till now we were not lucky in this way. But it's difficult because I tried to adopt the findings we had on ceramic materials, and ceramic is a brittle, pure elastic material, and I tried to adopt it to resin composites, and this is very often done in literature. And this might be right for fast fracture because we have only a neglectable part of plastic deformation or something like that. But under fatigue conditions, it changes. The polymer network somehow degrades under cyclic loading, and there's coming so many different influences in the microstructure of the material, which makes it difficult. Not difficult in a fast fracture to see what we have seen it in resin composites as we do it for ceramics, but for fatigue we do not see much. So.
I have a question following Jason's question, and a fast fracture versus fatigue fracture surface. And if you bring up the PowerPoint slide, I see the specimen preparation are very different in these two cases you showed. Fast fracture, you have beveled surface, you have chamfers, corners, but the fatigue specimen, they are sharp corners. And it looks to me it's initiated from the corner.
You're right. This is a mistake I did because I selected for this presentation. I selected pictures which clearly show what I would like to point out. It's as it is, but we have seen the same mechanisms if we use the same material. We normally bevel the margins of the material, and I just used this slide from a different study. But we do not see differences in strength if we bevel or if we do not. It is completely different in a resin composite material. On some point we were surprised. There could also be a huge pore in the tensile zone of a specimen, and it does not fail, but it does not fracture from the pore itself. So there are somehow more microstructure-related phenomena going on.
I like the diagram where you have shown the stress-strain curves. And certainly people think for these composites they will fracture in a brittle mode. But the diagram you showed, the curve is much more resembling to the metals. You have an elastic deformation first, and then it switches toward viscoplastic or something, which is a very characteristic for metal, for it.
That's right.
And the question is now, if you release the stress, you will have a permanent deformation afterwards once you reach that yield stress, like in metals?
That's one thing we can say from nano indentation measurements. You can see very clearly what happens in the polymer phase, in the matrix of the material. And once you wait a while, you don't see any permanent plastic deformations. So it's kind of viscoelastic. It has a memory, somehow a memory effect coming back to the original dimensions.
And that must be temperature sensitive, I would guess. I'm not a polymer guy, you know. So.
But of course, you're right. Yeah. And this is a huge problem you have with this provisional crown and bridge materials, the PMMA materials, because they are so low in modulus that they, well, it's on some point it's out of the limits for the fracture mechanics you apply.
Just one more thing. It also relates to the Nick's work. Once you have these nanoparticles, the fillers, and the smaller they are, the more they will tend to agglomerate, and the more difficult they will be to disperse. And obviously, you showed one fractograph, one fracture surface, clearly showing an agglomerate of those nanoparticles. Is that a common observation what you made, or how homogeneous these materials are?
Quite homogeneous, I would say.
Quite homogeneous.
Yeah. Well, it's not the question of, in my opinion, it's not the question of the nanoparticles itself. It's the question of the hybrid. Well, you have bigger particles together with the smaller particles. And the smaller particles, they need to be dispersed within the holes of the bigger particles. And as far as I can say from our findings, they are quite good dispersed.
I was pleased to hear you say that all of the action in the fracture seems to happen in the resin matrix. And that's again with this denture tooth, which for us was a brand new material to be working with. We saw, like you're saying, and also like Nick was saying, that especially in your case, the single load to failure, the monotonic testing, didn't predict at all what was going to happen under fatigue. And we have done a lot of work with fatigue of titanium and titanium alloy implants, and we clearly see a strain rate sensitivity in the titanium alloy, so that if you strain it at a low strain rate where you have dislocation motion work hardening mechanism, you see a very, very different failure and an earlier failure than if you go so quickly, like 15 to 30 hertz instead of 2 hertz, where now the dislocation motion thermodynamically is not allowed. It's shut down. And now you have a twinning mechanism for the work hardening, and it's more difficult to embrittle that alloy. But in either case, you have a little bit of embrittlement in a small volume of metal that then breaks brittly, and then you start to get your fatigue crack. This is what we see in PMMA also, and it's probably seen also in the resin portion of a composite. And we found literature that says yes, indeed. I mean, it's not well understood, but polymer scientists are guessing that you're starting to get chain alignment. You may be getting some crystallinity developing molecularly within the polymer, and you are embrittling the polymer locally, so that analogous to a metal, your initial event is a brittle fracture in an embrittled part of that material. And so I'm glad I'm believing you. You're saying that we're coming to the same conclusions here. So it's fun to see it applied in a composite at that very, very fine detail of where did the crack grow.
There may be also another aspect of that, may be the water absorption. You talked about the water absorption being diffusion limited.
Yeah.
And seems that after some time, 90 days, there's no difference between the materials. And so it would be interesting to see if you did a high cycle fatigue, some 1 million or more cycles per specimen, if that would allow the fatigue crack to propagate more slowly, allow the water time to diffuse beyond the crack tip continuously, and then maybe you will be fatiguing an entirely different material, like a plasticized material to some extent.
Yeah. We haven't done that until 1 million, but this is takes you a long time.
Hi, Ulrich. Okay. Well, very nice presentation and very informative. So I have one question and one comment. The question is, with the 10,000 cycles that you did in fatigue, clinically, what sort of service you would expect it to be, or you would think it might correspond to?
This is a very difficult question. I cannot answer. To be honest, I cannot answer. There are some estimations in literature you can find, as you can find it for toothbrushing and so on.
Yeah.
But this is not realistic.
Oh, good.
Yeah, we were surprised, and that's a question that we thought was going to bother us in this denture tooth work. But when we took a look at the probability of failure versus number of cycles, if you assume that 1 year is 500,000, 1 million, or 1.5 million cycles, it doesn't shift it very much because there's such a strong curve or strong knee in that probability of failure versus cycles curve. So the question becomes less important than we thought it would be.
Okay. Okay, great. Thanks. My comment is, going back to the viscoelasticity, we did a lot of work on static creep and on the same materials, and we get identical curves to what you got. So we got the elastic part, and then we got the viscous part and deformation there. When we measured, and we did see plastic deformation in those materials, although they range from very small, like 0.2% in some of them, to up to over 2% in some of them.
2% is a lot.
It is
quite a lot, yeah.
It depends a lot on the materials. So when you moving towards flowables, then you're getting
could be different, yeah.
Could be different.
I agree.
Yeah. So.
Ulrich, you showed with your data that fatigue testing and static testing show different behaviors, right? We know with nanocomposites that the flexural strength, for example, of these materials is as good as any microhybrid composite. But if you think about the particle size and even shape, you might think that the nanoparticles might not be as efficient as a toughening mechanism as a large irregular filler. So my question is, do you have any experience in terms of fatigue testing with those nanofilled composites? Are they as good in fatigue compared to microhybrid, compared to, as they are in terms of static strength?
Well, that's a good question, really. In my opinion, they are even better, the nanocomposites. Not because of the nanoparticles, because of the volume that is filled by particles. The elastic modulus increases and the strength of the material increases. I have shown few materials which have a really high strength and fatigue resistance. And these are on the market, these are the materials which are the highest filled materials, let's say. The problem is with bigger particles,